and use it, and that took some skill and training, but I've never had a case where the answer wasn't in mathematics. And I think you will find this too, and we want to give you the tools to do that. A second reason is that there are no functional programming classes at Duke except for this one, and it's one of the mainstays of computer science. So I want you to learn something about functional programming. Basically, it's vital for how to use lots of computers at once. So MapReduce, Hadoop, in industry and academia, it's really the only viable technique for using thousands of millions of computers at the same time. So we have to understand it, but we need to understand it using mathematics. And we need a language or calculus to understand functional programming and parallel programming, and that's what we'll teach you, among other things. It's also a great introduction to logic. It's mathematically quite interesting. And we need to be able to prove propositions, prove things about our program, so we have a basis of this class in doing proofs related to computer science. And Scheme is an embodiment of a nice functional language that's easy to learn, so there's a direct path from Scheme to functional programming to MapReduce, which we want to teach you about. So those are some things that we hope to tell you about in the class. During this lecture, I will, ordinarily, as you can see from behind me, I have these nice blackboards. This is a background of my classroom. If I had 8 blackboards, I'd leave things on the board and point to them. I can't do that as easily, so what I've done is I've taken some screenshots of, for example, some of the code and major results, and I'll try to flip between them a little bit. So don't get too dizzy when I do that. We'll see how well that works. And let's just review a little bit where we were from last time philosophically. So we had this notion that there's this thing, which is really mathematics, declarative knowledge, like what is the specification for what a square root is? And then we had something like a computational process. So this is algorithmic or imperative knowledge, so how to do things. So mathematics is what is, algorithmic knowledge is how to do it. And we also talked some about how to go back and forth between those two things. So declarative is a description of what it does. Imperative is the recipe for how to do it. And we need to understand both of these things. And you know from experience that going from the what to the how isn't always that easy. That's what programming is really, being a good programmer, but it's not as easy to go in the other direction either. It's hard to understand going from code to what it does, and it's very detailed, and it doesn't necessarily reveal what it does in a straightforward way. And we want to give you tools for moving back and forth between these two things. So we started talking about a functional language Scheme a little bit, and there's a mantra that you can get up and recite before you brush your teeth every morning, which is, in Scheme, everything is an expression, and every expression has a value. If you're ever confused, say this to yourself 5 times before asking a question. Of course, you could always ask me questions. Remember, everything in Scheme is an expression. Every expression has a value. Everything in Scheme is an expression, and every expression has a value. And with this, I think you probably won't go wrong. Okay, so that's sort of our wrap up of where we were philosophically, and now I want to go into a few more details. The course webpage is up. Try to read it every day. Lots of assignments, notes, and lectures and things like that. And we want to continue with talking in more detail about this notion. And I want to now switch to using a tablet so I can annotate that, and we'll also use the document camera a little bit, hopefully without knocking it down. So give me just a minute while I switch, and I'll be back with you when I get the tablet hooked up. So if all is going well, let's see now. All right, sorry for the feedback. I'm an engineer, so there's always going to be that problem. So if all went well, you should be able to hear me, and you should be able to see something about lecture 2. Can someone confirm that they can hear me and that you can see the shared screen?
Yes and yes.
Okay, thank you. Appreciate it. That's good. Very good. Okay, so in order to help you while we're having this remote instruction, I've tried to write down everything I will say so you can look at it later. And I will try to move along to something interesting technically. So today's main topics are here. By the way, there's some reading. This is a place where the textbooks are really good, in addition to handouts on the web. So these things obviously are over here. There are some nice reading in SICP, Able Set Assessment. I encourage you to read it. Having taught this course and having had a lot of undergraduate TAs, I understand that there's a trend to try to do material like this without doing the reading, but in this case, the reading will be very useful as it is in almost any math class. So today I want to talk about a few things. I want to talk some about logic. So, discrete math has a logic component. The logic will be delivered via the Lambda Calculus. And I want to talk about a little bit functional abstraction, which means procedures, and the substitution model, which you all have been thinking about some in even looking ahead to problem set 1. And 2 more special forms defined in Lambda we'll talk about. We already reviewed this. Again, I want to make the point that we need a calculus for computation. So the extraordinary effectiveness of the physical sciences, this is mostly physics, but also physical chemistry, physical biochemistry, parts of engineering, is because of Newton's calculus, which is a way of predicting the future and describing the past and the present. So Newton's calculus is to the physical sciences as the Lambda calculus is to computing. We need to learn the Lambda calculus. And so far, in writing a little bit of code, I've kind of waved my hands, talked about the evaluation process, that this expression returns this, one returns 14, and so forth. I'm going to stop waving my hands now and do something quite a bit more rigorous, namely the substitution model. So this is a formal way of understanding scheme expressions, at least once without assignment, and you won't need assignment for a long time in this class. So here's the way, thinking about what we're doing here. It's a little different from what you've seen before, but I think you'll probably like it. So what is a procedure or a method in sort of the object-oriented paradigm? I mean, how do we think about that? So a procedure does 2 things, really. It packages up a computation and it puts a black box around the operation so you can use it later. So in some kind of strange way, right, times xx is squaring. This doesn't really make sense, right? And similarly, averaging might be divided by plus xy with 2. Again, it's not quite right because what are x and y in these cases? So if you want to package up squaring or averaging for later use, you have to do 2 things. You have to tell it what variables are involved and what order they're in and so forth. So squaring involves 1 variable x. We'll write the code in a minute. So to package up in scheme, we use a special form called lambda. And I will often write this using the Greek letter, which is also how we write the Lambda calculus. And in fact, in Rapid, if you want to hit a few control characters, you can actually use lambda, but real programmers spell it out. So here's the key thing. Lambda makes the procedure. It doesn't name it. So scheme is very rational. And whereas other terrible languages do these things both set out. So define names things, lambda makes for an oriented world, and that's a fine place to be. You could think of there being a class of things, class of objects called procedures, and lambda is the constructor that makes one. So you'll see lots more about this in the demo and recitation on Friday, but here's how we would make a procedure to square things. Doesn't name it, makes the procedures. This returns a thing of type procedure. So basically, here's how it works. Lambda is a special form. It says make a procedure. This means it has 1 parameter x of type number, and this is the body. So this is the expression to evaluate once you've got x in some sense. And of course, you can read this somewhat informally as the procedure. Lambda means the procedure, taking the number x as a single parameter and returning the value of the expression times xx. So here's some things. So number is one of the types that you can use in Scheme Swindle. You can also write things without types. We think the types help make the code more readable. Each parameter has a type. So the Lambda form by itself does no computation at all. What it does is it creates an object that can do the computation later when it's used, in the first position of an expression. And the computation happens when it's applied. And applied means it's used in the first position in a combination. So Lambda has now come into its own, and instead of being some strange thing that only theorists use, it's in lots of places. It's in Python, it's in Java. These make an object called a closure, which is basically the implementation of a procedure. Neither Python nor Java does it quite right, which is one reason we don't use it. But it's sort of close enough, and you'll see them there, and it's kind of the same creature. It doesn't have the scoping right in those languages. So let's look at a simple example. Suppose we were to have divided by 0, 1, right? So this divided by 1, 0, right? So this returns an error, right? You get a divide by 0 error because it's trying to divide 1 by 0. But, and that's not good. By the way, some notation for this. One thing we can do is we can say this returns this value here. This is the inverted turnstile. It was created by Dana Scott, who essentially won the Turing Award for inventing the symbol. It means an error. And if you like and want to shock your parents, you can tell them this is called Scott's bottom, because it's called Scott's bottom operator. So this returns an error. But this beast here, lambda nil divided by 0, 1, this is not an error yet, because all this returns, I'm sorry about the scrolling, all this does is return an object of type procedure that when applied will cause the error, but it's not an error yet. Now, how do you actually make it produce an error? Well, you have to apply it. How do you apply a procedure? You put parentheses around it, and after it's arguments, it has no arguments, and so it looks like this. So basically, this makes a procedure, lambda nil divided by 1, 0. This returns an object of type procedure. That's fine, there's no error there. The procedure that divides 1 by 0 is not an error. But once we apply it to no arguments, then we're going to get an error. This is going to return an error. So note there's no naming as part of creating procedures. Creating a procedure using Lambda returns an object of type procedure. It's completely separate to name procedures. That is done using define. Okay, good. I think I'll skip over that, let you cover that in section maybe. So remember, in Scheme, everything in Scheme has a value and everything is an expression. So the Lambda returns this procedure object as its value. It's a method of doing the computation at a later time, puts it in a box, encapsulates it. So here's the cool thing about Scheme and some other good languages.
We do have a question.
Yes.
We do have a question about how do you apply the procedure object when it's not named.
I'm sorry, your voice quality is when it's not named?
Yeah. How do you apply the procedure object when it's not named?
I just gave an example that we can look back on, but I'm going to give an example that's a little less strange in a minute, and I think that will help. And if not, please ask me again about the question, okay? All right. Okay. Because we just did apply that procedure, but it's a little subtle because we're trying to get an error. So I'll give an example in just a minute. So as I was saying, procedures created, in fact, here's where it will happen, so you don't even have to wait very long. So just wait just 1 second. Let me just finish this point, and we will absolutely address that question. So when you create a procedure using Lambda, it's a first-class object. You can use it any place you use other values. So you can do anything with it, has all the rights and privileges of any other value. So you can give them as arguments, you can return them from functions, you can store them in variables, you can put them in data structures, all this stuff. They're just like 1, 5, 17, 2.174. And here I think I'm going to try to answer this question. Please let me know if I'm not clear. So by the evaluation rule, we know how to use a procedure object. You just put it in the first position of a combination. So this can be tedious to do over and over, so therefore we have define, which lets us name it. So here's how we would define the procedure for squaring and use it. So notice what happens here. This creates an object of type procedure. This applies it to 5, by which we get 25. Now, substitution semantics comes to the rescue here. You don't need to know that to appreciate the following fact. I can also use define. So again, in this next statement, the lambda returns an object of type procedure. Define then binds it to the variable square. Now we can say square 5. This will give us 25. So the thing is, these two statements are exactly equivalent in terms of what they do. And so that's how you would use a procedure. This is how you would use a procedure without naming it. This is how you'd use a procedure with naming it. Does that answer the question we had? Excellent. Thank you, Michaela. Okay. So we can now use square very conveniently. Again and again, we can square 5, we can square 3, we can use it like this. We can square 2 and square 3 and add them together and get 13. So now that we've defined it, we have we can use it lots of different places, just the same way we use any primitive procedure. Now I did see a question, why would we ever want to give a procedure that didn't have a name? So I'm going to give some examples where that makes a lot of sense. But the thing is that a lot of intermediate values don't need names, right? Like imagine you're writing a derivation in mathematics and you have a right-hand side of the equation. Why should you give that a name each time? So it makes sense to give it a name if it has some abstraction, but you might just want to define it once. So there are many cases where it can be convenient to have a procedure that doesn't have a name, and we'll do some examples of that fairly soon. But the main reason is that conceptually, there's no reason for every procedure to have a name. Like every value doesn't have a name either. So for example, suppose I were to look here at 2 and 3 and so forth, those don't have names, right? So same way that every value doesn't have a name, every procedure doesn't either. It turns out to be extremely useful to have this be separate. But that might not be clear until I give some examples, which will be in a couple of lectures. But feel free to ask more. Okay, so now we know how to make procedures. Actually, that's it. Make procedures and name them. So that's actually very quick. And now we've progressed. We can now try implementing the Heron algorithm for square root, which we had last time.
There's a quick question.
Yes?
On specifying the type of the arguments, is that always necessary?
No, it is not. Thank you for asking. So you can always write these things without types. The types kind of help you see what the types are. And in some instantiations of scheme and more advanced languages of type inference like ML, it will actually do type inference and type checking that can help you. So for now, think of the types as a way to help you see what the types should be and to annotate your code. But the code will run without it. So for example, let's go back to our square. So we actually have two examples here that I can do. So we first did square back here, right? Did we do square? I thought I did square without a lambda. Of course I did. So here's my definition. I'm sorry you couldn't find it. Here's my definition of square that has types in it. Does that make sense? Here's my definition of square which doesn't have types in it, which was here. So this one doesn't have types. So both of them are fine. In some sense, the one with types only works for numbers, and potentially the one without types could work with other things like complex numbers, or it could work with matrices. I mean, so there might be reasons to do it without types. So yes, you can do it either way. We recommend types because we can see what types you intended. Okay. So now we can write up the square root algorithm by Heron of Alexandria. Kind of cool. It has these parts here. And as I mentioned, what I did is I wrote these up. I also screenshotted this, so we should be able to flip back and forth as we look at code later on. So the top level here, we're going to remember how Heron algorithm worked. We're going to try 1 as our first guess. The try algorithm is going to see if the guess is good enough, and so forth. Then we have a predicate for good enough, a function here to improve the guess, and average, and we have the square function, which I've just typed in again for you. And notice here I did it without types. Okay. So as we look through this, there are a couple of things to note. So the first is this is a recursive definition, right? So it calls itself. So try calls itself. Now, that's something to get comfortable with in this language. We'll see later that this is actually an iterative procedure because there's no state built up on recursive calls. This will be a key theme of this course, to look at tail recursion, which compiles efficiently. So this use of recursion is more like loop or while or do. And a paid commercial advertisement, there's a huge difference between recursive definitions that syntactically call themselves like try above and recursive processes. We'll look at that in very soon in another lecture. Okay. Now, we have a new thing in here that some of you have already been looking at on Piazza called if. It's a special form. I'm going to come back to it later. I think you kind of have a handle on if, but I do want to mention that we have if in here, which we haven't talked about in lecture before. Okay. And as we look through this code, you can kind of get an idea of what the processing is like. Like if we look at this, let me actually see if I can flip back and forth as I promised I'd be able to. We have this, and we'll go to, see, got all my pictures here, not just these. So here's the code. I want to be flip back and forth between this. If you look at the code, you kind of get an idea of the flow of this kind of, you can trace it out a little bit. I'm not saying this is formal, but the argument you'd be making is, if we try square root of 2, it's going to first call try with 1, 2, and then it's going to check good enough. Is it guess good enough? It's not, so then it tries to improve it, try improve, causes improve with 1 over 2, averages 1 and 2. That's going to return 3 halves. It's going to try 3 halves as a square root of 2 and so forth. And I went through this quickly because this is all very fuzzy, right? This is all pre-theoretical, intuition. We can be lots more precise about it and get a better understanding of what the scheme expressions do. So the substitution model is a model of the evaluation process. Again, evaluation is defined as reducing an expression to a value. So that's what we want a precise model for when we could implement. So we have a handout on this today. And I want to tell you a couple of things just to get you prepared. So this is a tool. It's a model to understand values. What do the values of procedures compute? It's not what the computer does. Like the computer computes the same values, but there are more efficient ways to compute those values. So this is mathematically what the value has to be, but there's more efficient algorithms that compilers use. So what we have to do is we have to treat this model as a semantics, that is the mathematical meaning of our procedures. And then when we write code to compile the procedures, we have to prove that that code returns the same thing as the mathematical model. For now, we'll work with the mathematical model, not with the compiler. I want to go to the rules of the substitution model, which I've highlighted colors to make it a little bit easier. Let's take a look at it and see if that will work for us. So this is interesting because we have kind of two mutually recursive procedures called eval and apply here. So I've simplified this a little bit, but this is all the expressions here will be compound expressions, i.e. there'll be a bunch of scheme things surrounded by parentheses. So you're applying the first to the second. So the eval rule is to evaluate an expression. First, we evaluate all the sub-expressions, then apply the procedure object, that must be the value of the leftmost expression, to the remaining values called the operands. Now, apply is right down here. So how do we apply? How do we do that? So to apply a procedure object to a set of arguments, first we evaluate the body of the procedure with each argument substituted for the corresponding parameter. And we'll do lots of examples of this, but these are the rules that we'll flip back and forth. So first, the eval rule calls the apply rule. It also calls the eval rule, right? So here, eval, to evaluate, and it calls apply. So eval calls itself, eval also calls apply, and then, of course, apply calls evaluate too. So we have to get comfortable with this notion of mutual recursion. And in fact, you can implement all this stuff in Scheme, which is kind of cool. But that is the model for the meaning of your programs. And those are the only rules other than a few special forms. So at this point, an example would be helpful. So let's do that. So we need some notation to be able to do this. So rule 1 will be evaluation, and I'll use parentheses for that. And for the application step, I'm going to use brackets. And that's fine because in our version of the code, brackets aren't used. And I want to distinguish between objects that have already been evaluated and objects or symbols that need to be evaluated by drawing a box around them. So 5 is a symbol, but 5 with a box around it has been evaluated. Now, you want to type sometimes, and so will I. And so for a thing with a box around it, you can use curly brackets like this. And I will do that too. These are exactly the same. So for those of you who are very interested in the distinction between these things, 5 is actually a symbol. It is a symbol that represents or points to a mathematical encoding in the computer of the number 5. That representation could be binary, could be hexadecimal, could be, have the least significant digits first, the least significant digits last, doesn't matter. But the actual Platonic object 5 is the thing that is in a box, the actual representation. And if you think that 5 is actually the number 5 rather than representation thereof, these conventions are made up by mathematicians, right? There are conventions for these things. So you're allowed to name your function whatever you like, but we would never say let 5 be a function. So continuing, so by the way, this is our substitution model. We have it again here. Continuing with this, star is a symbol, but when evaluated is something like mult, an internal encoding of a procedure. These are distinct entities. We need a notation for procedures too. So if we have a lambda expression that's going to return a procedure, this returns, how do we denote that? Well, that's going to return a thing of type procedure, proc, and it's going to have some parameters, and it's going to have a body. And we draw a box around it to indicate that it's evaluated. If you are typing, you can use curly brackets instead. So note, proc is not part of Scheme any more than mult is. There are notation to indicate a procedure object as a value. So let's do an example. Here we have an anonymous procedure that adds 5 to its argument. So this returns an object type procedure. That's going to be this thing here, proc, an argument list, which is a number called x, and plus x5 is the body. So that says this says it's a procedure. These are the parameters. There's just one. This is the body. Okay. So that's the only rules we need. We have the rules for, we have all the rules for the substitution model. We have some notation for it. And now I want to do an example, namely an example involving square. All right. Was there a question that came by, or was that answered? From Dominic?
Oh, yeah, my question was just when you, like, let's say like in the assignment, we're taking in lambda as a variable in another lambda, we're taking in a procedure. So the variable type for that procedure would be proc and not lambda then?
Yeah, you're not ever taking in a variable called lambda. You're taking in a thing of type procedure that the lambda expression returns.
Okay.
We would think of that as type function. I mean, okay. I would say the type would be function because everything's function in Scheme. So yeah, the lambda expression always returns a thing of type function, namely a procedure object. And that's the type you would use. Yes, Michaela, perfectly right in your comment. Okay, so I want to do this both ways, both by typing and by writing. So I'm going to switch to the parallel document camera that I knocked over twice last time. And you all can relax a little bit while I hopefully don't amuse you with that. So hang tight for a second. All right, so I should be back. Please let me know if you can see the document camera and you can also see me.
Yep, you're all good.
Oh, that's good. I ordinarily would be very worried about having dead air during a class, but I feel that it's not so easy to pay attention to these long lectures, and maybe a little break isn't so bad. Okay, so I wanted to switch to the camera for a couple of reasons, the document camera. So reducing an expression to a value is a lot like doing a mathematical proof. And for that reason, I want to signal to you that doing this is something that can be done usually with pencil and paper or pen and paper. And that's a great way to do it. You can also do it typing into text. And in fact, one thing that we'll learn in this class is that really without approximation, that programs are proofs and proofs are programs. And this viewpoint actually led to most of the breakthroughs in cryptography, networking, and our internet infrastructure today. But let's take a look at it in a simpler case here and try to look at reducing expression to value. Our first example of really using the substitution model. So I put the substitution model up here. Let's see, was there a question? Sorry. I saw a question fly by in chat, but I didn't see what it was. All right, so let's do a simple example of trying to evaluate the square of 5. So remember we had before define square, and I won't use types, lambda x times xx. So as before, as I described, this will return a thing of type procedure that gets bound to the value square. We can use that any place we would use any other value. And now what we're interested in doing is we're interested in evaluating what happens when we say square 5. That's our start. So this is an expression. So coming up here to evaluate an expression, first we evaluate all the sub-expressions. Okay, easy enough. So what's the value of square? Well, the value of square is a procedure object. We have a notation for that. Procedure, the parameter list is 1 long. The body is times x. And I'll put a box around it to indicate that it's an evaluated value. We evaluate 5 and we get 5. So we evaluate all the sub-expressions, then apply the procedure object that is the value of the leftmost sub-expression to the remaining values. So how do we do that? I'll indicate that we're in the apply stage now with brackets like this. So I want to apply the procedure object that has to be in the leftmost place to the remaining values. There's only one remaining value, so I'm ready to go. So now I'm in step 2. How do I apply a procedure object to a set of arguments? Well, what I want to do is I want to evaluate the body of the procedure with each argument substituted for the corresponding formal parameter. So let's write out the body. If I had an eraser, well, let's actually have an eraser and do this. See if you can see this. So I'll write this out. Times xx, this is the body. So this is our body written in pencil. So substitution, you can think of this as a form of erasing. So I want to substitute the corresponding parameter for the arguments here where they occur. So you can think of substitution as being, get rid of these guys here, these x's, substitute in the value 5 for each of these guys. So now we're ready. So what do we do here? To apply a procedure object to a set of arguments, namely a list of one argument, the numeral 5, evaluate the body of the procedure, which was times xx, with each argument, namely 5, substituted for the corresponding parameter, in this case x. So now we get this, and now we have to evaluate, we're back to step 1. Now we have a nice expression, we want to evaluate this. We do step 1 to evaluate expression, evaluate all the sub-expressions. Let's do that. What's star? Well, that's just multiplication. 5 is already evaluated. 5 is already evaluated. And now we're ready to do an application. Okay, so pretty good. So at this point, you know, we're doing pretty well with this, but at this point, we're beyond the substitution model, right? We're beyond the rules because mult and 5 are primitives, right? All that the substitution model does is tell us how to reduce expressions to values, and these are all values. So each primitive operation in some case has its own special case rules. In this case, mult simply performs multiplication, returning our value 25, and we're done. And that's our first example in lecture of using a substitution model. And I just wanted you to see that because it's, I think, pretty convenient to do this sometimes by hand on paper. For longer things, we might want to type them. All right, any questions on our first example of using a substitution model?
Why did we box everything again?
Every value that has been evaluated gets a box around it. That tells you you don't have to. That tells you you don't have to evaluate it again. It's already been evaluated. It means it's a value, not an expression.
Do you always have to evaluate something before you apply it?
Yes, if you, well, you do, because otherwise you don't know what its value is. Remember, in Scheme, everything is an expression. Everything in Scheme is expression, and every expression has a value. So if you don't evaluate it, how would you apply it? So that's the argument. So yes, you do. So in other words, I can't apply this lambda because it isn't a thing. I have to evaluate the lambda, get a thing of type procedure, which is this, and then I apply it to 5. Great questions. More questions? Is multiply a proc? So mult is a primitive. It's a primitive procedure in some sense. So these proc things, these are what technically these are called compound procedures. Namely, they're procedures that are defined by the user, right? So you can get into these things and you can look at their arguments, you can look at their body and so forth, and you can do manipulations on them. Primitive procedures just have a specification, right? They just say mult. So mult is definitely a procedure, but it's a primitive procedure. Two types of beasts here: primitive procedures, compound procedures defined by the user. So in other words, suppose you're working with a partner. Partner makes square. You can look at his or her code and you can see what it does, and you can do substitution model. If your partner uses mult, you can't look at that code. You just have to go with the specification you've been given for what mult does. More questions?
I couldn't really tell when looking at the written out equation. In the part that's boxed where it says proc x, and then it has the 3 symbols in the second part, is that xx lambda?
Oh, yeah, let me write it a little more clearly. I can see why that would be a problem. I'll just write this again.
Thank you.
This is the star symbol for times. Proc x times xx. How's that? It's also in the lecture notes, of course. You can take a look at it there.
Thank you.
Good. More questions? All right, how about we see a more complicated example? One question for Moses. I didn't quite catch what that was. Someone want to repeat it? Abe is answering that. Let's go look at a more complicated example, unless there are any questions you'd like to ask now, which I'd be happy to take. All right, good. Well, we'll go over to the tablet and give me a minute, relax for a second, and we will resume in All right, I'll switch back to the tablet to do a little more with you. Tell me, can you see my screen and can you hear me?
Yeah.
Good. Thank you. Thank you, Robert. Thank you all. Okay, so here's what we want to do. We want to try some of Heron's square root algorithm. That's a more complicated substitution model. We'll use the substitution model. So I'll flip back and forth between here. And I want to start by talking just, talk a little more about if, since you guys were interested in if. Let's talk about that a little bit as we do this. Just because we need a semantics for if. So the thing is, we must have a semantics in order to actually understand what's going on here. So let's go back to if on our tablet. Take a look here. All right. So we've seen define in Lambda. And you've been looking at if, I know. It's kind of similar to other languages. But if has this form, if it has three parts. There's if, which is a sort of like a keyword, then it has a test, a consequent, and an alternate. It's a special form. It does not follow the usual evaluation rule. And the evaluation rule would be evaluate all the sub-expressions, then apply the first value, which is the operator, to the remaining values. If has a special rule instead. It says evaluate the test, which is here. If the test is true, evaluate and return the consequent, which is here. If the test is false, evaluate and return the alternated, which is here. So it only evaluates one arm, and this is super important. You wouldn't want to do both, right? So the example usually given, although it's a little bit gruesome, is suppose we were to say if threat launch missile, otherwise keep watch. So a very military application, but that's okay. So think what would happen here. Right semantics is if some threat, you launch a missile, right? If there's no threat, you just keep watch. If this had the usual semantics, what would happen would be you'd first evaluate all the sub-expressions. So if might return some value, I don't know what it would be. You'd evaluate the threat, that would be true or false, who knows what that would return. Then you'd launch the missile, then you keep watch. So you don't want to do both branches. Okay, so as it turns out, we have true and false in scheme. Any other thing is also true. The only thing that's actually false is the false value. And so there's some subtlety here, but the if kind of does the expected thing, but you have to follow the special rule, right? If you want to evaluate an if statement, we have to use the special rule. We evaluate the test first. It's either true or false. If it's true, then we evaluate and return the consequent, otherwise the alternate. And we can go into more detail about this. All right. And there'll be an example with if as I do this next substitution model example. I do want to make one comment here. So we just did this. By the way, my handwriting was inadequate, and we want to look back. I did also type out my proof here for square, and that's in the notes. And I do want to say that this is like a proof, and our derivation here really is a proof with some assumptions, right? So this is in some sense a proof that square applied to 5 returns 25, right? So there's a connection between what we're doing in understanding our programs and mathematical proofs. All right. And I hope questions on if you have them, you'll mention them, or it will become a little clearer by looking at our example. All right, so here the limits of our technology may be reached because I want you ideally to be considering the code while we look at the derivation of the substitution model for what value the code returns. And I've tried to set that up here a little bit by being able to flip back and forth between pictures. And I'm going to do this when we need to look at the body. So the main thing we need to do is when we are applying procedures, we need to look at the code or remember it in order to remember what are the parameters and what's the body. We have to copy them down. And in fact, thinking about it as a copying operation is really not such a bad thing. All right, so with your permission, I will now go ahead and do a more complicated example. This is designed so that we should be able to get through a little bit of it and do the rest in section. So ask any questions you might have. So let's do the example of square root of 2, right? So how do we do this? So first, let's just refresh our memories. This is an expression, and I'm going to remember how to do this, but I'm going to look back to my pictures. How do we evaluate an expression? We evaluate all the sub-expressions, then we apply the procedure object that's the leftmost thing to the remaining guys. Okay, good. So let's do that. So what happens here is that square root is going to evaluate to this procedure object here. And 2 evaluates to 2. Why does square root evaluate to that procedure object there? Well, because that's how it's defined. Look over here. I called it Heron square root here, but we could easily fix that. So to make the code run, we'd have to call this square root. But you see, Heron square root is bound to the thing the Lambda returns. The thing that Lambda returns is a thing of type procedure. And you can see that it's going to have one parameter, namely x, which is a number, and a body, which is try1. So that's why this works. So now we've done the first step of the, we've done the eval part. We evaluate all the sub-expressions. Now let's look back at our model. Now we're in the apply stage. So to apply procedure object, which is the leftmost thing here, to a set of arguments, we're going to evaluate the body of the procedure with each actual argument it's substituted for the corresponding formal parameter. So let's do that. So first, let's get our types right here in terms of talking about it. In thinking about this, I will just say that one of our terminologies, we call x the formal parameter, and we call 2 the actual argument, right? So we're going to do a substitution. So in order to get to step 3, we have to look at the body, which is this beast here. We write it out like this, and what we've done is we substituted the actual argument for the formal parameter. So now we're ready to do the eval step again. We're evaluating this beast here. All right. I'm going to do more, but I'm going to pause to ask if there are any questions, because this just repeats for all of these things. I'm going to do them, but I want to see if what I'm saying makes sense to you. Any questions? Please ask if you do. I reversed those so that we can tell the difference between a notation for mathematics, which is our proc thing, and actual scheme. So if you look at one of these, you can immediately tell not only from the proc, but from the notation that it's not actually. Whoops. So try is this procedure here from our code, right? So try is defined to be this guy. So what try, I mean, you can ask what try should really do, right? You can ask what it really should do here, but try is supposed to, check if the guess is good enough and then improve it. But we want to see if this really works using our substitution model. So this is implementing Heron's algorithm, which we described or sketched before. Good. All right. Let's go on. Now we're at this step here. We want to apply try to 1 and 2. All right. So this is a standard evaluation step. Again, I don't have to flip through every time, but I will do it. What's an evaluation step? Well, to evaluate an expression, in this case, try 1, 2, we're going to evaluate each of the sub-expressions, namely try 1 and 2, then apply the procedure object, that's the value of try, to the value to the remaining values. So let's do this. Try will be this procedure object here. Now notice I've used an ellipsis because I don't want to write out the entire body, but we can look up the body. 2 is already evaluated, so it's 2. 1 evaluates to 1. So now we're ready to do the apply stage. So let's look back on how we do an apply. And I want to point out, I'm making this sound mechanical because it's completely mechanical. If you know all the rules, we can absolutely reduce expressions to values at this point. So remember what we're trying to do is we're trying to actually apply this procedure object here to the values 1 and 2. So how do we do it? To apply a procedure object, this thing here, to a set of arguments, in this case the set 1 and 2, we evaluate the body of the procedure with each actual argument substituted for the corresponding formal parameter. Let's look at what we've got here. This is our procedure object. These are our formal parameters. These are our actual arguments. This thing here is the body. Are you wondering what the body really is? Well, we can look at the code. That's the key thing. The code is everything in here after the lambda. It's this if statement here. So now we're ready to go. And we're going to try to actually evaluate this. By the way, all these notes are on the web, and look at them again. So the body looks like this. If good enough, 1, 2, return 1. Otherwise, call try on improve 1, 2 to approximate the square root of 2. Reading it inside out, if 1 is a good enough approximation to the square root of 2, then return it. Otherwise, what we do is we first improve the guess, namely we try to improve on the guess 1 for the square root of 2, and then we recursively call try again to get the square root of 2. As you might guess, 1 is a poor approximation to the square root of 2. We want to actually show that. Now, if is a special form, so we have to handle it specially, but we just went through that. What we're going to do is we're going to evaluate the test first, which is this thing here. So let's evaluate the test, and that's down here. This is just an expression, good enough applied to 1 and 2. Let's look at the code for good enough again, which is over here. So what good enough does is it's basically checking whether or not the absolute value of the square guess minus x is pretty small. And it's doing that as a predicate. So that's what good enough is doing, and that's what that body is. The body's indicated with an ellipsis here because I just wanted to write enough so we could tell what body it was. Oops, sorry about that. Okay, so how do we evaluate the test? Well, good enough, 1, 2. This is a standard expression. Again, let's go back to how we evaluate expressions. To evaluate an expression, evaluate the sub-expressions, then apply the procedure object. That's the value of the leftmost sub-expression to the remaining values. Let's do that. We have good enough, 1, 2, and here's what we get. Good enough is this, I'll write it on top. Good enough is this procedure here. It's a procedure object. Notice the curly brackets. And it's being applied to 1 and 2, which are the actual arguments. So now what we do, and again, let's beat a dead horse, it needs some more beating. Let's go back to our rule for apply. To apply a procedure object, and that's indicated by the square brackets I used. To apply a procedure object to a set of arguments, evaluate the body of the procedure with each argument, that is actual argument, namely 1 and 2, substitute it for the corresponding formal parameters, namely in this case, g, the guess, and x, the thing we're trying to square root. So let's do that. What I've done here is I've just written out the body like this, and I've substituted, let's actually look at the body. So look at the body, it's got these g's and x's in here for good enough, right? It's got the guess, it's got the x, that's fine, no problem. So what I'm going to do here is I'm going to instead substitute in 1 for the guess and 2 for the x, and I get less than absolute value minus the square of 1, which is going to be 1, minus 2 is that something that's very small. Now, I have dots here because what I'd like you all to do is to work that out, not necessarily in real time here. And if you work out the steps of the substitution model, you will prove that this eventually returns false. So this then has the value false as desired. And if that's hard, please ask questions about this in either after class, or you could ask questions in section and we can work it out in detail. But I want you to do that little task. So now by the special rule for if, we evaluate the alternative because it wasn't good enough. So now we have this form here, try, improve 1, and so forth. So I've just copied this down here. I've taken it out of there. And now we're going to do more substitution model. So once again, we're back to the eval step. We have an expression to evaluate. How do we evaluate an expression? Again, same rule. To evaluate an expression, evaluate the sub-expressions. And then apply the leftmost one to the rest. So let's do it. This is a little trickier. We have to do it inside out to get all the values. But it's pretty straightforward when you think about it. So what happens here when we do this is, obviously try here is going to give us a procedure, right? That's fine. And then 2 is going to give us 2, and then improve 1, 2 is going to give us some value probably. We don't know what the value is. So what I want to do here is I want to think about this by showing you how we think of it this inside out. Like obviously, this guy here is going to be straightforward, right? In some sense, I mean, this guy here is going to be pretty straightforward, but the thing is that the improve maybe not so straightforward. So let's look at this here, and what I've done is taken this out here. So what I've done is I've taken the improve because I want to go into detail about that. And that's because the try will be easy, the 2 will be easy, the improve we have to like do another kind of level of thinking. So what have I done here? I've basically just taken improve 1, 2 and applied the first rule of the substitution model. So let's do 2 things. Obviously, the substitution model says evaluate all the sub-expressions. But to see that I did it right, let's look back at the code, which is here. Here's improve, kind of cool here. Improve takes 2 parameters, a guess and a number. It averages the guess and what happens when you divide x by guess. So that's what the body is. So now you can see that this looks basically correct. This thing here is the procedure improve. I have 2 formal parameters, guess and number, and then I have that average and the rest of it in there. These are the actual arguments that will be substituted. Now we're at the apply stage. I will go back to showing you this. Maybe the last time I'll show you this, I'll just name the rules. Apply, to apply a procedure object. We instantiate the body of the procedure with each actual argument substituted for the corresponding formal parameter, and then we evaluate that then. So that's what I've done here. Notice here is the body. What I've done is written out the body here like this. Average, I have average, and now I substitute the actual arguments, which are here, for the formal parameters, which are here, and I get average 1. That's the first argument. The second thing is divided by 2, 1, like this. Let's take it one more step. I now have a standard expression, which is average. To evaluate this, I have to evaluate all the sub-expressions. And so here I have the procedure for average. So average expands to this, the procedure for average. And 1 expands to 1, it's already evaluated. And when you divide 2 by 1, you get 2. So now I have 3 values, a procedure object, which is going to do averaging. I have 1 and 2. Now I have to evaluate this, I have to apply this. So how do I apply a procedure object to a set, namely 1 and 2 of parameters? I instantiate the body of the procedure, which is divided by plus AB over 2, like this. And I substitute 1 for A and 2 for B, and I get this creature here. I get divided by plus 1, 2 divided by 2. And again, an ellipsis. If you work this out by the substitution model, you'll see this returns 3/2. So now we've evaluated every sub-expression of try, improve, 1, 2, 2. Namely, try is this procedure object here. It's just the procedure object for try. 2 is already evaluated. It's this thing here. And by this proof here, we just showed that this guy returns 3/2 or 1.5. So we have everything we need to do this. We substitute back into the body of the procedure with values of 1.5 and 2. And we're back at, get something that looks a lot like step 4, which we had over here. And the pattern repeats. So now we have this case here. The test is again false. So we're going to try to improve things again, and we're going to continue. So now I'm going to give you some things to think about and leave some time for questions. So how do we want to think about this? So I would view what I have here as a proof using the Lambda Calculus that improve 1, 2 returns 3/2. And similarly, you can frame what you're trying to do with the substitution model as a theorem or a small claim or proposition, namely this. So what you should try to do is use the Lambda Calculus just as I did, and as your TAs and classmates are doing, to prove that try applied to improve of 3/2 and 2 to approximate the square root of 2 evaluates to the value 1.41667 or something very close. And if you look at the sketch of the proof that I give you here that you should try to complete, it's broken into subpieces, but they're things very similar to what we did. Like, for example, we're going to have another case of running through improve like this. And then we're going to substitute back, and we're eventually going to try to see if it's good enough, and eventually it will be. And then we'll get an actual proof at the end, and you can write your 2 lines. So with the substitution model, we have a very precise model that lets us determine the values of expressions, which is actually pretty cool. And as we do this, I promise you that this works for everything in Scheme, with the exception of a few already. We did this all without any. So assignment is like changing the values of variables. We didn't need to do that. So without assignment, we actually have a semantics that is a meaning for all the values in Scheme, and we can figure out what our programs do and prove that. Now, when we add assignment, the substitution model breaks. We need a more complicated model that's called the environment model. We're not going to cover that in this class. I just covered it in later classes, but it is in Abelson and Sussman, and if you've read as far as you will read, it would be an easy extension for you to think about. And we won't do any assignment until the very last week of class, where I'll show you some fancy data structures. Okay, so we did a lot today. In fact, we did some proofs, somewhat more interesting proofs to computer scientists, perhaps because they prove what programs actually do. So what did we cover? What are kind of the high points? And then I'll see if there are any questions. We recapped the evaluation rule, and we have 2 new special forms, define and lambda, and a new special form if, simple if then else conditional. We talked about what procedural abstraction really is. So if you're an object-oriented type of person, you can think of lambda as the ultimate constructor. It returns an object of type procedure. So lambda can be thought of as make procedure. And in the same way that we don't think the text make window, make hash table, make display option is actually anything other than a means to return the object that's a hash table or an iterator or a window. Lambda's meaning is to tell the interpreter return a procedure. So lambda means make procedure. So lambda builds the box. Naming is a separate issue. You can associate a name to any value using define. Having done this, we defined a formal model called the substitution model, based on Alonzo Church's Lambda Calculus. And there are 2 basic rules: to evaluate an expression or combination, and to apply a compound procedure, one that we have defined. So a very astute question was asked earlier. We only have this semantics for applying compound procedures defined by the user or by some code that you're reading. For things that are built in, you have to look up the manual to see what they would do, because they're not covered by this. All you can do is say that the specification for multiplication is to multiply 2 numbers together. But for anything for which there is code, for anything defined in Scheme for which there is code, there is a lambda that defined it, there is a list of formal parameters, and there is a body. And when you have those things, you can use the substitution model to figure out and calculate what it will return. So it's an operational embodiment of the Lambda Calculus, and that's used to model our computational processes. So the great thing is that after 1.95 lectures, you actually know the Lambda Calculus. And it's one of the triumphs of mathematical logic. It lets you let people prove the limits of logic and computability. Very important part of discrete mathematics. And it's closely linked to the meaning or semantics of computer programs. Now, of course, saying you know it is not fully accurate. You know, I could teach you the rules of chess or Go very quickly, day, perhaps an hour, but you wouldn't be a good chess player, good Go player very quickly. With the Lambda Calculus and with Scheme and functional programming, you'll be an expert after a semester, which is really quite an accomplishment. So in telling you that you know this, there are no more rules to know, but there are lots of subtleties and lots of practice we have to have. This will let us prove our programs are correct. We'll know what values they return. So the process of understanding our programs is very similar to writing a proof. So we're going to try to be more accurate and get closer and closer to the truth as we do that. So with that, I want to close on time and stop and ask if there are any questions, which I'm more than happy to take. And also, I will stick around in this Zoom meeting if there are questions after class, if you'd like to discuss anything related to this or anything else. So what do you think? Does it make sense? Do you get it? Ask me any questions you might have.
So when you say lambda calculus, what exactly does that mean? Like, obviously there's this lambda operator that outputs a function, but what exactly did Alonzo Church sort of discover that sort of completes this lambda calculus?
Yeah, that's something that we'll learn in the course of this class. Sorry to scroll. So basically, in the substitution model, these two steps are called beta reduction and alpha renaming. And there's a third thing, it's related to gamma, that we won't use in this class. So the lambda calculus is these steps. And then the question is, what can you do with it? So what Alonzo Church did with it is he proved a version. So there are three allied deep results that happened around mid-20th century. There's Alan Turing's halting theorem. There's Alonzo Church's uncomputability theorem, and there's Gödel's incompleteness proof. So we have this trifecta of Turing, Church, and Gödel. And you can sort of prove the halting problem or undecidability using the tools of the lambda calculus or using what are called Turing machines, which are another abstraction that Alan Turing invented that's somewhat more operational. And these are also related to problems introduced by David Hilbert. So basically, what I can promise you is that using these techniques, you can prove the limits of what can be represented and computed, namely, can you have programming languages or formal systems that are complete and consistent. It turns out for our purposes, we're going to use it in a slightly different way. So Church, in some sense, used his powers not for ill, but to prove what could not be done. But we can turn it around on its head, and we can use the lambda calculus to prove what our programs actually compute, so use it in a positive sense. So we will mostly use Church, namely the lambda calculus, which are these two rules. This is the lambda calculus, to determine the values of our programs and expressions. So we'll use it in a constructive sense. We'll have these team up to prove the halting problem and some other problems. But we need both Turing's ideas and Church's ideas to do this. So on the positive side, that's the plus. We can get positive results, and we can see that our programs really do to return the values that we hope they will. On the negative side, we can prove things about the limits of computation, namely that there are problems that are very difficult or impossible for computers to decide. So the remarkable thing is that you actually know the lambda calculus now, and the first half of the course will be applying it both in the positive sense, what do your programs mean, and by lecture 13 in the negative sense, are there things you can prove there's no algorithm for? So that's a little preview of what we'll see before. Other questions?
I have a question. My question is similar to his. I don't really understand what's so special about the substitution model. Because the substitution model just seems like mathematics first evaluate what's on the inside and then go on the outside, or it just seems like PEMDAS or a convention. So what's the significance of it?
Well, perhaps it's in another way. With other languages, you don't have this. Other languages generally don't have a semantics. So in Scheme, we're able to actually do proofs about what these things mean. So you may have been taught something like tracing through your programs before, but generally, unless you're working in ML or Haskell or Scheme, your language doesn't have a semantics. And so that isn't rigorous, and neither is tracing pseudocode. So the point is that the scheme code is almost exactly modeled by the Lambda calculus. And so it tells you what your expressions mean. Whereas if you take a language like Java or Python, which are fine in their own, C++, we don't really have a semantics, so we don't have a way of doing that. Anything you say about it is sort of an informal statement. So it's the difference between having a mathematical proof about what your programs mean and having sort of a manual that you look up that tells you approximately what it might do. On the other hand, there probably are a few students that are very sophisticated that have seen a semantics for language before, in which case I would simply say this is the semantics for scheme, so we know what our programs will do. But what we want to do is we want to have the ability to prove theorems about the correctness, completeness, and complexity of our code. And the Lambda calculus is the mathematics that lets you do that. If it seems simple, then I count that as a success. But it's very powerful because it will work for all our programs. And we'll see more about that later in the class.
Thank you.
Sure. So we're 2 minutes over. So what I'd like to do is I will end this part of the class for now. But what I will do is I'll stay, and maybe some of the TAs will stay also, and we will take, I will take questions, or just if you'd like to chat, I'm happy to do that. So I'm stopping the recording if I can figure out how to do that. Let's see. Have I stopped sharing my screen?
Yes.